Alright, hello everybody, and today we're going to be having a look at how we can represent our trigonometric functions, namely sine, cosine, and tangent, on a unit circle. So used to thinking of using these three functions on a right-angled triangle, but we can actually squeeze them out from a unit circle, and I'll show you how. So consider some angle from the x-axis. Let's call this theta, for example. And you see this line right here that makes this angle with the x-axis goes up to some point on our circle right here, our unit circle. And in fact, when we're working in radians, whatever number this angle is, let's say it's pi on 3 radians, the arc length along the circle right here will be the exact same as that angle. So if we have pi on 3 radians right here, that means the arc length here will be pi on 3. But let's say we want to define the coordinates of this point right here on our xy plane. So how exactly can we do that? So if we want to find the y value of this point, what we're considering is how far up it is. So we want to find this length right here, and if we want to find the x value of this point right here, we're considering how far along the x-axis it is. And you may notice that we have exactly a right angle triangle right here, and that's where our sine and cosine come in. So we don't know what these two lengths are right here. Let's just call them x and y for now. And maybe we want to relate x and y to theta, since we have a right angle triangle here, and we can use all of these functions right here. So in this right angle triangle right here, also notice that the hypotenuse is exactly 1, because the hypotenuse right here is exactly the radius of the circle, but the radius of the circle has a value of 1. So our hypotenuse here is also 1. So let's go ahead and try and find what x and y are. So if we want to find what y is, how exactly can we do that? So you see we have three values to work with. We have this angle right here, we have the length we're interested in, and notice that's opposite of that angle. And then we also have the hypotenuse right here. So that should kind of remind you of sine, because sine is exactly opposite over hypotenuse. So if we use that, we're going to get the sine of our angle theta right here being opposite over hypotenuse. So it's exactly y over 1, which is exactly y. And similarly for x is the adjacent side to this angle, and we know the adjacent and the hypotenuse, so we can use cosine for that. So the cosine of theta is exactly x over 1, and that's exactly x. So you see, sine is exactly the y value we're looking for, and cosine is exactly the x value we're looking for. So in fact, we can replace these x's and y's with sines and cosines. So the height of that point is exactly sine of theta, and the x value of that point is exactly cosine of theta. So in fact, if we call this point P right here, we can say that its coordinates are, well, the x value, which is cosine of theta, and the y value, which is sine of theta. And if we know what theta is, we can find what point this is on our unit circle by just taking the cosine and the sine of that angle. So that's how sine and cosine are represented on a unit circle. But how about the tangent? Well, to represent the tangent on a unit circle, we have to know one little fact, namely that the tangent of some angle theta is exactly the sine of that angle divided by the cosine of that angle. And if you want a little bit more intuition on why this is the case, remember that on a right angle triangle, tangent is opposite over adjacent, and sine on a right angle triangle is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And notice these hypotenuses cancel out, and now we have both sides of the equation being the same thing. So tan is exactly sine over cosine. So if the tangent of some angle is the sine of that angle over cosine of that angle, remember before that we can kind of think about sine as being the y value and cosine as being just the x value. And you see we have y over x right here, and that's kind of like rise over run, because y is the rise, x is the run, and you see rise over run, that's pretty much the gradient. So pretty much the tangent of some angle, that can be represented by the gradient of this line right here. So if you can calculate the slope of this line right here, then that just gives you the tangent of theta. So that's a nice way to think about tangent, just the gradient you get when you have an angle of theta right here. So using all of this knowledge, namely that sine of theta is the y value, cosine of theta is the x value, and tangent is the gradient, we can better visualize what kind of values we get when we plug various values of theta into these functions. So let's just do a couple of examples just to play around with these ideas. Let's take, for example, the angle theta being equal to pi over 2. Well, where exactly is pi over 2? Well, we know a full revolution around is 2 pi, which means that if we go only halfway to 180 degrees, that's pi radians, but we're dividing this by 2. So therefore, pi on 2 should lie exactly here. And what if I asked you, what exactly is the sine of pi over 2? Well, remember the sine is the y value, and if you move your little line from the positive x-axis all the way up to pi on 2, well, what exactly is the y coordinate of this point? Well, that's exactly 1. And how about the cosine of pi on 2? Well, remember cosine is exactly the x value. So if I start here and I move all the way up to pi on 2, what's the x value of that point? Well, it's just 0. And how about the tangent of pi over 2? This one's a little bit trickier because we have to think about gradient. So if we start here, we move our line up, well, our gradient is going to get bigger and bigger and bigger and bigger. Then we're going to end up with this line right here. But the problem is this line has an undefined gradient. So therefore the tangent of pi on 2 is undefined because it's just a straight line up. You can't actually calculate the gradient of this thing, and you can check that for yourself by using the fact that the tangent is the sine over cosine. 1 over 0 just blows up. So let's do another example. Theta being equal to pi over 4. Well, we know pi over 2 is right here, and pi over 4 is exactly half of that. So instead of going all the way to pi on 2, we're only going halfway to pi on 4, and that's exactly 45 degrees. So for the sine and cosine of pi on 4, you can just use your exact value table for that. So sine of pi on 4, that's just root 2 over 2. And because 45 degrees is right in the middle, you get that nice symmetry where the cosine of 45 degrees is the exact same thing. And if you imagine moving this line over to 45 degrees, you're going to get a triangle that looks like this. It's going to be a right angle triangle. This will be 45 degrees. This will be 45 degrees. And you can use some symmetry to prove that this length is exactly this length. So the sine, the y values, is exactly the same as the cosine, which is the x values. And how about the tangent of pi on 4? Well, tan on pi on 4, remember, you can think about that as gradients. So when our angle is pi on 4 out here, 45 degrees, well, notice that our rise is the exact same as our run. So that means we're going to get a gradient of 1. So tangent of pi on 4, that's exactly 1. And a nice little trick I like to use when I think about tangent as a gradient is when I have tan of pi on 6 and tan of pi on 3, because I always got to get confused between whether it was root 3 over 3 or just root 3. And when you think about this in terms of gradient, it makes sense because tangent of pi on 6, it's all the way down here. So that means it's going to get a smaller gradient. So tangent of pi on 6 should be the smaller values out of these two. And tangent of pi on 3, that's a much steeper gradient. So it's going to get a bigger value for the gradient. So that's a nice way to remember the exact values for tangent, because you can get confused between these two values quite easily. So yeah, that pretty much does it for today. Hope you guys enjoyed this video, and I'll see everyone next time.